Hello, everybody. Welcome to the webinar from Alethea Communications. And the topic, as it is clear from the slide, we are going to discuss MLO and latency in Wi-Fi 7, mainly some experimental results that we have done experiments in our lab. I would call them the early experimental results. And we should probably follow it up with another webinar with more stuff. With this, I would like to say good evening to people from East Asia. Good afternoon for people from India. And good morning for people in Europe. Okay. The webinar is going to take about 1 hour's time, but let's say we would finish the presentation in 50 minutes or so, and we have 10 minutes to answer any questions that you may have. Even during the webinar, it's possible that you can post your questions, and the Alethea team would answer some of them, and some would be left for me to answer towards the end. So feel free, even if the questions are not answered, we would send out the answers to your email address after the webinar. Be assured that we are tracking every question that you are actually asking. With this, I would just like to introduce myself. I am Ramakrishna Chikala. I'm called Rama, and I'm the product manager in Alethea Communications. So let's start with the main thing that we are going to discuss, which is the multi-link operation, or MLO for short. This was the promise of MLO in Wi-Fi 7. What did it say? So this is the screenshot that I use it very often in the presentations. And this is from the Wi-Fi Alliance brochure. And it says multi-link operation, or MLO. The benefit is deterministic latency, increased efficiency, and greater reliability. So this is talking about latency. It means the latency has to be very low. Increased efficiency refers to the throughput. I mean, you should be getting more from less. And greater reliability refers to the fact that it should work for large number and probably in conditions which are, I mean, stressed out, or things that are not normal. And this is supposed to be achieved across home, enterprise, and industrial environments. So this is the promise of MLO. And like you, we are also wondering or checking, is MLO really living up to the promise? Okay. And as I said, this is an early experimental result. And from our, what I would say, experience, it is in the positive direction. So let's see now if MLO is living up to the promise with the experiments that we have done. Before I go to the experimental results, I just want to give a little bit introduction on the MLO types and where we are with respect to the deployment in the market. So I hope everybody knows that the device that supports MLO is called a multi-link device, and it's otherwise called MLD for short. Now, there are two types of MLDs. The first one is multi-link multi-radio. This means that the device, it can be an AP or a client device. These devices do really have two physical radios that are used for the multi-link operation. Now, there are three types of multi-link multi-radio devices. One is called simultaneous TXRX, which is otherwise called MLMR STR. And these days, people just shorten it to STR. This just means that the TX and RX can happen simultaneously on both the links. So there is no restriction per se for the transmission or reception on any of the links or channels or bands, as you may say. In case of the second type, which is the non-simultaneous TX-RX or MLMR and STR, there are some restrictions in the sense that you can only transmit on two links simultaneously or receive on two links simultaneously. You would not be able to do the way or the way flexible way in which the MLMR STR works. Then the third type is called EMLMR. So enhanced multilink multi-radio TX RX. The word enhanced here refers to the fact that the device can listen to control messages on a different channel when compared to the channel on which the current transmission and reception is going on. So this capability actually makes it enhanced. And yes, there are devices that can do enhanced multi-link, multi-radio TX-RX. The other type is the simple one. It's called MLSR, multi-link single radio. But in this type itself, there are lots of devices. So this is, I would say, more closer to the traditional device where there is one radio and it takes some amount of time to switch to the other radio. And it's most likely that a lot of devices would be in this category of MLSR. But the more interesting or exciting thing is the EMLSR. So EMLSR, again, the word enhanced refers to the fact that the device can receive control messages on the other channel while transmitting and receiving on the current channel. So why is this exciting? It is exciting because it provides the cost efficiency of an MLSR device, and it would provide in some ways the benefits of the multi-link, multi-radio devices. We would see more of it in the subsequent presentation, and I would also explain the MLMR, STR, and EMLSR in a little more detail. I would just like to leave a word on the type of devices currently in the market. Most of the devices, most of the access points do support MLMR, STR, and EMLSR, and maybe probably EMLMR as well. And everybody supports MLSR. We don't have real devices, client devices with MLMR and STR, but it does not preclude that it won't happen in future. But we would revisit it at a point of time when this has become really prevalent in the market. For now, I would concentrate on MLMR, STR, or STR for short, and the EMLSR device types. Let's do a little bit more, and then we would come back to the experimental results. As the slide indicates, so we have just completed the recap, and I would now explain the components and test procedure and follow it with the MLMR experimental results with interference and EMLSR experimental results with interference, and what is our future expectation with respect to MLO and what's going to happen. And in the end, there would be a question and answer session. A portion of the recap is still pending, but it's just that I'm going to do it just immediately. So here we have MLMR STR operation, and you see that this is, I would say, a fictional MLD device with MLMR STR that is actually able to transmit and receive in 3 links. I'm saying fictional because most of the client devices that are available in market today only support 2 links. So it is able to transmit on these 2 links simultaneously and receive on this link. And if I look at the color code here, so we have 6 gigahertz, 5 gigahertz, 2.4 gigahertz. So it is able to transmit and receive in all the 3 bands. and the arrows indicate the direction in which the transfer is happening, and they actually have no relation to each other. In case of NSTR, these arrows would all have to be in the same direction. So this is the flexibility that is provided with MLMR STR, and it's probably the more complex of everything. If I go back to how the message exchange or the actual transfer happen, I would want to represent it here. Assume that the link is currently free on link 1, which is the 6 gigahertz band. So the transmission happens on 6 gigahertz band. Then we have an ACK for the transmission that has happened. And then the channel is busy for some time. Then the device would continuously do clear channel assessment. And when it gets the opportunity next, it would do the transmission. Then this would be followed by an ACK, and it's again busy, and so on. So if this is the way the normal transmission for a single link would happen. And if we talk about latency, because latency is our topic of the day, so the amount of time the channel is busy would actually determine the latency foreseen. The reason being that the transmission would invariably need a response from the application level, and it would not be possible if the channel is busy. And hence the latency here involves the busy time of the channel. The rest can be ignored because you have some procedure to do, you need some time to do channel assessment and so on. Now, take the case of the multi-link scenario. Here, take the link 2. So we assume the link 1 is still the same for the purpose of illustration. And so now assume that the link 2 is busy initially, and then it gets free. So there is transmission here, followed by an ACK, and link or channel 2 is busy, and then you again have transmission, and there's an ACK. Now, as you can see, there is an opportunity to transmit here, and there is actually opportunity to transmit here. There is an opportunity to transmit here, and there's an opportunity to transmit here. Given that we actually have 2 channels to play with, the opportunities for transmission is higher. And given that the busyness of the channels are random, it's possible that you may always get the other channel free. So now the latency measurement, if you do with the MLO, would be lower. See, this is the premise in which the MLO is designed, and is supposed to give us deterministic or lower latency compared to the normal case. So as you can see, the L2 is surely smaller than L1 in this illustration, and we should assume that this would be the case even when we really use it in the field. The next one would be EMLSR. So just to give a little more context to all of it, when I say the control message here, the control message refers to the RTS CTS sequence or the MU RTS CTS sequence. The main capability of the EMLSR device is the fact that it can listen to the other channel as far as control reception is concerned. It can also do clear channel assessment on the other channel. So this is done in various ways or implemented differently in different devices. But the crux of it is this, that the full TX RX can only be done on one channel, and clear channel assessment and control reception can be done on the other channel. So why do we need this? This actually helps us to switch the channel. The control message in this case is the required stuff that we need to switch to the other channel. So if I plot, if I go through this, you see that there is control message in parallel. There's no problem. So if we go back to our illustration, so when there is only one link, you have transmission, you have an ACK, then it's busy. We have transmission again and an ACK. and it's again busy. So this we have gone through before, and we know what is the latency. Latency is the amount of busy time that you have on the channel. And now if we have two links, so we have transmission and an ACK, and at this time channel 2 is busy. Then when channel 1 is busy, we have the availability of channel 2. So this is the thing that everybody should understand. So we have a sequence RTS CTS. Actually, if it is coming from AP, it would be an MURTS and a CTS sequence. And so this helps the receiving device to switch the channel. So because the receiving device is always capable of receiving control messages, once it receives an RTS, it sends a clear to send message and then switches the channel to receive the data. So if we compare with the MLMR STR case, there is this additional signaling that is needed in EMLSR case to switch the channel. Obviously, the transmission is not possible on both simultaneously, which is the case because of a secondary radio being available with MLMR STR. Now, if we go through this, when it is switching from channel 2 to channel 1, again, we have the control sequence, which is the RTS CTS. And then, yeah, so this is how it works. And then you have another sequence here for switching the channel, and then there's a channel switch, and it works. Later in my presentation, I would also provide you a glimpse of how this happens via a Wireshark graph that we have made to illustrate this purpose. So this is the crux of how EMLSR works. So the latency L2 is obviously lesser than latency L1, and it looks very similar or close to the latency that we have seen in MLMR STR case. So except that we actually do have an RTS CTS sequence, which would take up some time. Okay, so this brings me to the test setup that I would like to present. So in this test setup, we have an AP MLD for the purpose of the test, because all the client devices only support 2-link MLO. We are only considering 2 links for the test. And so one link is in 6 gigahertz, the other link is in 5 gigahertz. In the first set of experiments, we would actually use an interference generator that is shown here. This has 3 radios, and it can generate interference on any of the bands with any of the bandwidth and to the extent that you would want. So it can generate interference anything from 0 to almost 100%. We would also use a multi-band sniffer just to check that the MLO transmission is happening really in 2 bands, and the basic association is good as far as the MLO is concerned. On the client side, we use what is called the Wycheck MLMR STR client. And this supports, this is based on WCN 7851, and it supports 2x2. I would come to the details of this client just a slide later. And we would use iPerf, and in this case, we would use the version iPerf 2, which supports the burst latency and one-way delay for the latency measurement. I would want to emphasize the fact that the whole setup is actually in an RF chamber, and all the devices that are here are synchronized for time via the protocol that is called PTP. This is needed because we are actually measuring latency, and different devices having different times and not having time synchronization would affect the measurement of latency, and hence this requirement that all the devices are synchronized via PTP. So the interference generator talks to the interferer AP. So this is like, you have a parallel setup with our test setup. And this is the interference generator is needed, and and not some client to do the interference generation, because typically the clients which obey Wi-Fi rules or WLAN rules of channel assessment and back off would actually reduce their transmission once they see another device in their vicinity. So, for example, if I replace this with a client, this client will back off when maybe this setup client is talking, or the AP in this setup is actually transmitting. But the interference generator in this case would maintain its transmission irrespective of what other devices are doing in the vicinity. So that's the main reason why we need this interference generator. The AP and client configuration is as follows. So we are doing tests for MLO. So the client and the AP should support 802.11be. The AP is a 4x4 in each of the bands. And the bandwidth selected is 160 megahertz for 6 gigahertz and 160 megahertz for 5 gigahertz. The AP itself supports MLMR STR 3 links, but for the purpose of the test, 2 links is enough, and it also supports EMLSR. The client device is a 2x2, and it supports MLMR STR 2 links, and the bandwidth set to 160 megahertz. There is a particular reason why the bandwidth is set to the same value in both 6 gigahertz and 5 gigahertz. The reason being the TCP transmission efficiency is best if the channels are of the same size. If you have different size channels, the results of TCP are not, let's say, very intuitive for you to understand. We have not used 320 megahertz for 6 gigahertz purposefully, even though the AP and the client do support 320 megahertz. We have used, as I mentioned before, we used the iPerf 2 version, and I have the link to the external site at the end of my presentation in references section. So you can refer to it if you want to use iPerf 2. So the MLMR STR client actually supports 4K QAM 320 megahertz. We are using only 160 megahertz for the purpose of the test. It supports MLMR STR, and it supports all these traffic applications that include video streaming, HTTP, YouTube, speed test, VoIP, and FTP. And the device itself is backward compatible with all the legacy Wi-Fi technologies. The EMLSR client is almost the same, except that in this case, it only supports the EMLSR and not the MLMR STR. And this is also a 4x4, supports 4K QAM, 320 megahertz, and it supports similar set of applications like YouTube, speed test, VoIP, and FTP. So the interference generator actually supports all the 3 bands. So we have a tri-band interference generator, and the adjustable noise levels are anywhere from 96% to 2% across all bands, and it can do simultaneous transmission on all the 3 bands if needed. Yes, so, and then it is automation ready, and it has REST API and JSON APIs, to actually automate it for the test purpose. So this is the UI of the interference generator. So you select the band, and you can select the occupancy level. So when I say the interference level, this is the channel occupancy level. So we have calibrated the interference generator to occupy the channel to a designated percentage. So this is achieved with the proprietary change in software. So now we are coming to the real stuff in this presentation, the experimental results for MLMR STR with interference. The way I would go about, before I dwell on the results themselves, is that we always do a test with 0% interference to 80% interference. We would first introduce this interference on one channel And then we would do the same thing on the second channel as well. When we do the two-channel test, we introduce interference simultaneously. Okay, so I will come to it when I actually discuss that part of the experiment. So the first part of the experiment would be to actually do MLMR STR with interference in 6 gigahertz. At 0% interference, this is the kind of throughput value you would get. Again, let me be specific. The DUT and the client are at some distance in the chamber. And if you see the result here, the MLO off case performs lower than the MLO on case. But knowing that MLO on actually uses two channel, I would be actually expecting kind of double this throughput. So at 0% interference, it's not double, but MLO surely performs better than the MLO off case. And you can clearly see that as you increase interference, the MLO performance is better and becomes far better than the MLO of performance. So even though the difference here is not 100%, by the time it has reached the 80% interference level, this is double the MLO off case. So full, what I would say, credit to the MLMR STR. In this case, we do get the required throughput or higher throughput as predicted by, the design. So this case, I would call this as the TCP full buffer with HyperF2 case. Why would I say full buffer? Because we are trying to kind of pump full, or you are trying to fill up the channel as much as possible. It's not a case where you are only sending traffic with some Mbps and then measuring any stuff. Reason being, full buffer latency and non-full buffer latency would always be different. So in this experiment, we have chosen to actually give the full buffer latency. I do think that this would be the actual practical case. If we go to the burst latency has decreased by 56% by the time we have introduced 80% interference. What this means is that, given that this is an MLMR STR case, it has the second channel to transmit. If I introduce interference in 6 gigahertz, there's always 5 gigahertz to transmit. So it is expected, but it seems that the latency benefits are really pronounced for the case of, interference in only one channel. I do think this is expected, and most of us would not be surprised by this result. Next, okay, let me just tell one point. So what we measure here is called the burst latency. I would like you to refer to the HyperF2 documentation. So even for TCP, there is a measurement that you can do what is called the burst latency. And this is given out directly from the HyperF2 tool, and we are using it as it is. So we go to the UDP, and UDP also performs well with MLO on, and we do see a difference as the interference increases. The MLO case performs poorly once the interference increases, and MLO on case, since it has the availability of the second channel, it does well. It's similar that we still don't have 2x link performance, even though we have 2 links, and I would rather think that this is some improvement that would happen in future, and it's just that people are still optimizing the throughput for many of these devices. One-way delay is doing good, and for UDP as well. Why is this called a one-way delay? Because in UDP, you only have a transmission from one direction, reception on the other direction. There is no acknowledgement as such. So, this is one-way delay. And it is key that you actually have the synchronization of the time between the transmitter and the receiver. to actually get this correct. And this is the kind of delay we have in our system. MLO has lower one-way latency. The difference seems to be higher at higher interference. I do think this is on the expected lines, and it's kind of similar to the behavior of TCP. The next one is that you have interference on both links. Yeah, so this is, I mean, I would call the worst case scenario for MLO. So here we are actually using the interference generator as indicated to simultaneously transmit on both 5 gigahertz and 6 gigahertz. And we would introduce interference on both the channels to the same amount of channel occupancy. So if I do 20% channel occupancy on link 1, it would be 20% channel occupancy on link 2. And if it is 40 on link 1, it would be 40 on link 2. So this is to keep the experimental combinations in check and also understand how the whole thing is working. So with this experiment, we did measure the same thing that I have shown in the previous 4 slides. What happens to TCP throughput, what happens to TCP burst latency, what happens to UDP output, and what happens to UDP one-way delay. The rest of the instruments are same. We have a sniffer, we have a YCheck MLMR STR client, whose capability I have given it in the slides before, and we have PC with iPerf too, that is used to measure. So we have TCP throughput results here. You see that the MLMR STR with interference in both links, in this case, the throughput has increased, or I would say increase. The throughput did not decrease as badly as the MLO off case, and the difference is actually 154%. So MLMR STR case for a interference scenario on both the links at 80% has performed 154% better than the normal scenario. I think this is a very good result to show the benefit of MLMR STR, MLDs. I would like to just caution you that this is a single device test. So we only have one client device and one AP device. And it is to be seen how this would actually scale up when we increase the number of clients. I think we should keep that in mind. But otherwise, this is a good result for the MLMR STR case. How does the latency or the burst latency look? And the burst latency really looks good. If you see at 80% congestion on both the links, there is a 62% decrease in latency when compared to the MLO off case. I think this is actually a very good, I would say, advertisement for the MLO. It is kind of living up to the promise of lower latency at large amounts of interference or congestion from either neighboring PSS and so on. So what the key takeaway here is that the latency improvement seems to hold good even with interference on both links. We can go to the UDP case now. So in case of UDP, it's on expected lines. We do have the MLO off case doing better than MLO on case. Consistently, I don't see too much difference. I just want to point out that when we measured UDP good, it's the 0% loss UDP that we are talking about. So the values are of this order, and it does seem to perform, if not better than TCP, but almost equivalent in that sense. If you see the one-way delay, it's also the similar case. The MLO on case is really performing better than the MLO off case for UDP one-way delay, and equivalently better, I think. So this this is the, I would say, crux of MLMR STR results from the experiments that we have conducted. I just want to illustrate how this actually happens in real life with a graph from Wireshark. So those of you who are familiar with Wireshark, we do have IO graphs functionality in the menu, and you can use the IO graphs functionality and filter or color the 5 gigahertz packets by taking the MAC address that is relevant for the 5 gigahertz transmission and reception, and by taking the MAC address for the 6 gigahertz transmission and reception. And we can actually plot, and I have plotted it for a 1 millisecond interval, and this is how it looks. You see that the packets are all over the place, and this we have taken with interference at 50% level. So which means both 5 gigahertz and 6 gigahertz are exposed to equal interference. And you see that as and when the client or the AP gets a chance to transmit in any of the bands, it keeps going up and down, because MLMR STR by definition can transmit on both the links or listen on both the links at any point of time. So this is how the transmission pattern looks if you check the capture. With this, the MLMR STR experimental results are concluded, and we would now go to the EMLSR with interference. So again, I would just like to reiterate the AP and client configuration. So we have the AP, which is the same as before. It is a 4x4, and it supports MLMR, STR, EMLSR. We have kept all the other parameters same. And the client device, except for the fact that it supports EMLSR, it's a similar device. And this works in 160 megahertz for the purpose of this test, and is 2x2. So this is the setup for interference on one link, and this is exactly the same as before, but you need to note that the only difference is that the client is EMLSR, so the client can transmit or receive only in one band at a time. So we need to see how this makes a difference. And we do have an interference generator. We would do an experiment with one link interference and two link interferences. And then we have the interferer AP to which this interference generator talks to create the interference for the main setup. We also have a multi-band sniffer to again see, the association is proper and there are really packets transmitted on both the links and so on. So this is the EMLSR result that we got for the TCP throughput. And if you see that, the difference between the MLO off and MLO on case initially was very low. And this, I would say this is kind of statistical. I don't think it's supposed to be even higher as such. I mean, they should have been equal. As the congestion increases, the MLO on case clearly performs better. You see that this differs only by a small margin, and then the margin increases, and by the time we reached it, actually, this is 71% higher than the throughput that we got at 80% congestion on the link on the current link of transmission. So what does this say? This says that EMLSR is actually doing pretty well. I mean, given the fact that EMLSR would be a device with lesser cost and only one radio, it seems to hold off very well with interference in one of the channels. So it's kind of what I would say, proving that the design is actually working. Let's check the latency. I think the latency is again good. We do have the latency number decreasing from the MLO case, finally at 80% interference to minus 42%. So this is 42% smaller than this. So again, this is a good result for the TCP burst latency for EMLSR with interference in one channel, or in this case, it was the 6 gigahertz channel. Now comes the setup and the interference in both links. So this is very similar to the previous setup. And, the only thing is that now there is interference on both the channels that is generated by the Y-check interference generator. So this is how it is. You see that the EMLSR client with the MLO off client is performing marginally better in all cases. It is better, but not all that better. You see that the difference, even at 80%, is about 18%. This is the measured value that is represented here. So overall, it is good news, but it is marginally good. I mean, we don't see the kind of difference that we see with the similar case with MLMR STR case. I would compare that in a later slide, just a while. Give me a minute. And then we have the TCP burst latency, and TCP burst latency is also slightly better. And with increase in interference, it still seems to be slightly better. And at 80% interference, it is at minus 15%. So there is marginal difference in latency for the MLO client, and it seems to hold off. Let's compare this with an MLMR STR case, because I think this is where the picture would be more clear. So I do have the EMLSR case here, and I have the MLMR STR case here. If you see that EMLSR, this is interference on two links, so it performs marginally better, whereas in case of MLMR STR, it is really, really different. It performs really well. Again, for interference on one link, EMLSR did really do well, and it was almost close to the MLMR STR performance. But with two links, it seems that the MLMR STR performance is way better than the EMLSR performance. And we should think this is normal, because the EMLSR devices can only transmit on one channel. So the effectiveness of, or the efficiency can be only limited to that channel. So it's, whereas the MLMR STR has the other channel as well. And even though it is also subjected to interference, but there's a way to switch to another channel. So this kind of provides the distinct advantage that we are seeing from these graphs. This is the typical Wireshark trace for an EMLSR. And in this case, this is a case where there's only interference on one channel, which is the 6 gigahertz channel. And if you see that, even though we have actually introduced a lot of interference on 6 gigahertz channel, it keeps using this channel as and when it gets an opportunity to transmit. Again, this is based on clear channel assessment and so on. So EMLSR actually would look like this in real life. I have taken this from a blog my colleague in Alithya Communications has done. And yeah, so they had a PCAP and they could plot this with Wireshark IO graph and get this result. So it would be interesting for you also to see this stuff if you have a PCAP with an EMLSR client. So we are back to the summary now of what's happening. So the experimental results with one client show us that for an MLMR STR case, we have the improved throughput, improved burst latency for interference in one link. And we also have good throughput and really good burst latency even with interference in two links. Why did I give two thumbs up for this, even though the latency is decreasing? So is the fact that throughput increase with another link is quite reasonable to expect. But the latency decrease, even though we have interference in both channels, is actually the bonus. UDP similarly performs the same thing as TCP. And in case of EMLSR, you see that with interference in one link, it's really good. It's almost as good as MLMR STR. But with interference in two links, we have marginal improvement with respect to the MLO of case. And hence, yeah, I kind of put this arrow here. Yeah, it is good. But let's say when we compare to the MLMR STR, it's little less. So with this, I think we have come to the end of the experimental results, and I would like to just spend a few minutes on what we can expect in future. So I would expect, or we all would expect more efficiency of the MLO algorithm. Especially, I think we should expect 2x the throughput if we use two links and 3x the throughput if we use three links. Then we also have this thing. I don't know if in Wi-Fi 6 we had this feature which is called OFDMA. It was also supposed to give us lower latency and better efficiency and so on, but it took us a long time to get that in real life. We did also a presentation on that before, and we saw that the OFDMA really gives improvement, but for a limited number of clients. So the number of clients are usually, I don't know, something like 4, 6, 8, or maybe at best some 16. Post which we did not see a real benefit of using OFDMA. In case of MLO, the way it is seen today, I think MLO has, at least for the first experiment itself, I would say, it seems to be working well. And I would love to see the results for a large number of MLO clients. We do think that this number will be very high. And as we speak, our team is actually doing tests with many MLO clients. And we would probably present this in a webinar later, in the new year. The third point is that there would be uplink and downlink differences with respect to, I don't know, latency as well as throughput, because the MLO algorithm on the client device and the AP device would not be the same, and there would be some different levels of performance. We also have client preferences with respect to MLMR, STR, and EMLSR. So there are a lot of clients that are EMLSR capable. There are clients with respect to with MLMR, STR capable. So we really do not know which would prevail, or there will be mix of clients forever like this. But there will be some preference at some point of time. The last point, I think we have touched upon this even in the previous webinar. I think MLO would be really useful in mesh backhaul, both for throughput efficiency and lower latency. And the fact that you can actually get 2x, 3x throughputs also would make this a very good use case for mesh backhaul. So with this, we have come to the end of the webinar. I would like to thank the whole of Alithya team that has helped us to get this webinar going. I would like to take some questions that are answered or not answered as of now. So I have a question. Is there any preference if there are 3 links in scenario, if 2 links are available for TX and 1 link is CCAPZ? So if it is an MLMR STR case, I don't think it matters. whatever link is free will be used by the transmitter after doing the CCA. And it does not matter. I mean, there would be no preference. Again, I would put one caveat, that the MLO algorithm itself is proprietary. There is nothing open or prescribed by the specification. It is possible, I mean, it's a possible scenario. It is possible that you have a 2.4 gigahertz, 20 megahertz channel, and for whatever reason, the MLO algorithm do not like to select a 2.4 gigahertz transmission and keeps waiting for the 5 gigahertz or the 6 gigahertz channel to become non-busy. That's a possibility, but at a top level, there is no preference. Okay. Then I have a question. Does an EMLSR supported STA decide link switching on its own? Can the AP send a request to the client for link switching and all this? So again, this is done via the MURTS CTS sequence or an RTS CTS sequence only. And the transmitter can decide to send that sequence on the other channel based on the MLO selection algorithm at any point of time. So whoever, when I say whoever, whichever device is transmitting decides on the channel on which it has to transmit. And the only thing is that you have to give sufficient time for the receiver to switch the radio, and hence the requirement for this, MURTS CTS or RTS CTS sequence. Then there is another question: which MLO mode do STS in market generally support? The way it is currently, the Intel B200 supports EMLSR. Some other phone devices also support EMLSR. The high-end devices support MLMR STR normally. But it is different for different vendors. Some vendors support EMLSR on 5 gigahertz and 6 gigahertz. Some vendors support STR on 2.4 and 5 and so on. For multicast throughput testing, how much MLO will help in mesh design? And what are the config and parameters we need to enable or disable along with MLO? See, it is whether it is multicast or not should not matter for the purpose of MLO. I understand that multicast would be only there is only one transmitter. So the transmitter decides based on the channel assessment at the transmitter and transmits. And that there is some risk associated with multicast anyway, because different devices are at different place and they may have different error rate and so on. But MLO itself does not change anything with respect to multicast. Which mode is enabled as default in AP MLO? So generally, most APs would support MLMR, STR, and EMLSR. And obviously, the default case, which is the MLSR case. So I would say all APs would support MLMR, STR, and EMLSR at this point of time. Which RF sock are you guys using for AP and station? As I mentioned, the AP is a Qualcomm-based solution, and one of the clients is a Qualcomm-based WCN7851, and the other client is an Intel BU200-based client. Why do we see throughput gain with EMLSR? It's just that it is more efficient in switching the channel, and hence we should be able to see some gain, especially if both the channels are not occupied. I mean, meaning you say there is congestion on one channel more predominantly than the other, we should still see a throughput gain with respect to a client which is always in a single channel. So I think it is possible, but as I showed it in the results, with interference in both the channels, we see very marginal gain. So there is this question, if there is interference on both channels, how does it decide? No, it is not like that. At a specific instance, channel assessment is done on both the links, and whichever channel assessment returns good for the transmitter, it will be transmitted. Any change for WMM in MLO? I don't think there is anything to do with the WMM as far as MLO is concerned. Okay. I think with this, we come to the end of the presentation. As I mentioned, we would surely answer all the rest of the questions we did not have time to answer. And Alithia team would reach out to you and give you the slide set and the required references for the webinar. I would like to thank all of you for attending this webinar, and I hope it was useful, and we would come up in future with more testing on MLO and other features in Wi-Fi 7, and we'll keep you informed.